So the last time we spoke about how there were three options for reasoning. We spoke about how reasoning over OWL entailment over the full language is undecidable. And we spoke about three options. The first two being an incomplete reasoner that might sometimes miss entailments. A reasoner that's complete and accepts any ontology, but may sometimes never halt. And the third option of restricting OWL or not accepting all ontologies, rather accepting ontologies in a sublanguage that we know to be decidable. So this third option, we spoke about this already, that we can prove something is decidable. Is decidable by providing an algorithm for it. So in the description logic community, they've been looking at fragments of first order logic that are decidable. And the logic also in some way extends first order logic with things like transitive closure. But essentially, they've been studying fragments of logic that are decidable, that have decidable reasoning. So OWL2 full is the name of the unrestricted language of OWL. It's sort of using all of the features we've seen in any way you might like. Okay, so we'll accept an OWL2 full reasoner will accept any ontology. You can basically send any combinations of features you like. While OWL2DL, OWL2 description logics, is a restricted language that if your ontology is in OWL2DL, then you know that reasoning will halt and give the correct answer. So, okay. So what should we restrict to? Let's say we're given OWL full, and now we're given the task of, okay, design a decidable fragment of OWL full, OWL2 full. So what do we disable? Where do we start? Well, okay, the first thing is that when we did this proof of the undecidability of OWL, we know that if we can express this thing that encodes the tiling problem, then hey, there must be something here that's undecidable. So we definitely shouldn't be able to express this, right? So we must restrict something here, for example, but that still doesn't really tell us that it's going to be, the result is going to be decidable, right? It's possible that we could do such a proof, for example, in another way using other features. However, in the case of OWL2DL, what it restricts in this case is that functional properties can only be used on simple properties. So there's this notion of simple properties versus things like transitive properties or chains. Essentially, what we're not allowed to do is count properties that have, transitivity. We're not allowed to count properties that are used on chains. And that's what we needed here. How we're using it in the proof was to say that there's only one diagonal tile. And the intuition behind that is essentially that with this sort of counting of more complex properties, we can create more complex shapes of models. If we don't have this sort of counting, then we can't create grids. We can't create these sort of cyclical models. We can only create or enforce them. We can only create tree-based models, which is something important for decidability. So in any case, we'll come back to that. So OWL2DL here restricts functional properties to be used only be used on simple properties. Okay, so we can no longer express this here. We can no longer use this to express that each tile has one diagonal tile. So is this enough to guarantee decidability? Well, not really. We just know that this particular proof won't work, right? So there are other proofs. There are other ways we could reduce from the domino tiling problem, for example, to OWL without requiring functional properties, functional complex properties. So, okay, that's maybe not the best way to go about guaranteeing decidability. The better way would actually be to just give an algorithm, right? So we should give an algorithm that's sound and complete. So it always returns the correct answer and it always holds. So in terms of what OWL2DL restricts, and then we'll talk about the algorithms, it restricts functional properties to be simple. So we have no chains and no transitivity. So this is an important restriction. It likewise restricts properties that are used with has self or cardinalities or inverse functionality. Asymmetry and irreflexivity, they must also be simple. So we can't have use those properties as well in chains or transitivity. We need to be very careful to follow a specific RDF syntax that can be parsed into description logics definitions and axioms, and to explicitly declare what are classes, what are object properties, what are data type properties, and so forth. Object properties just means that it's something that typically takes an IRI, whereas data type properties is something that take data type literals like dates or booleans and so forth. So there's actually quite a lot of restrictions, and trying to give a neat summary of all the restrictions is actually quite messy. But these are some of the important ones here. So overall, these restrictions are designed to try to make sure that the models that are generated, we can create things like grids, or we can create things that are enforce models that are cyclic. We can always have these kind of tree-shaped models. But okay, so we have all these sort of slightly counterintuitive, difficult to define restrictions to make sure that the language is decidable. But the benefit of this is that so long as your two ontologies, O and O prime, follow the L2 DL restrictions, you are guaranteed a correct answer to O, to the question of whether O entails O prime or not. And not only that, but you're guaranteed a correct answer and the procedure will halt, right? So you can decide this. You can figure these entailments out. So in L2DL, we can get these sorts of entailments that we saw previously that were not possible from the rules. So Vincent is of type Godfather, person is equivalent to the disjoint union of criminal or lawful. Every person is either criminal or lawful. Godfather, something cannot be a Godfather and lawful at the same time, which tells us somehow, okay, Vincent then cannot be, if Vincent is a person, Vincent must be criminal, or lawful, it cannot be lawful, therefore must be criminal. So we infer that Vincent is a criminal here. So how could we implement this sort of procedure? How can we get these sorts of entailments, right? Well, we spoke about using rules, but if we wanted to cover all such entailments with rules, it'd be almost like we'd have to define an infinite number of rules to cover all such cases. So rather what we're going to do is, there are various algorithms we could use, but one of the most common is called the Tableau algorithm. And what the Tableau algorithm does is, instead of trying to decide this entailment of does O entail O prime, it uses unsatisfiability. So it adds not O prime to O to create a kind of new ontology. And it expands the knowledge using rules. So essentially, it then tries to expand whatever is known, looking for an inconsistency. So essentially, we negate O prime, we add it to O. So if we combine O and not O prime, then if it's inconsistent, this entailment holds. If we spoke about that before. So what we do then is we'll just be looking for some inconsistency. So what we're going to do is expand out all the knowledge we have. And in the case of multiple possibilities, try all possibilities, right? And just keep going until we can't really expand any more knowledge, or we found some inconsistencies. So how does this work? If and only if every branch is inconsistent, then in that case, O entails O prime. So when we branch, we're going to branch on all the possibilities that are created by these disjunctions, these different, like, for example, that Vincent is a person in one branch, Vincent is a criminal in one branch, Vincent is lawful in the other branch, and we're going to check that both branches are inconsistent. So, okay, let's see the example. So we have a disjunction here, which means that we have this sort of two possibilities going on. So we have this Vincent is a person, and a person is either lawful or criminal, right? Okay, so what does this mean? It means that there's two possibilities. Yep, so Vincent type lawful, Vincent type criminal. So how do we reason about these sorts of cases? Well, what we do in the Tableau algorithm is we just branch and we kind of look at all the possibilities. So what we've done here is, sorry, before that, we have O, our original ontology, and then we've negated O prime here. So not Vincent type criminal, right? And now we're going to check if this is unsatisfiable. It means, is this inconsistent or not? If we say that Vincent's not a criminal, do we find an inconsistency? If there is an inconsistency, it means that actually this ontology here entails that Vincent is a criminal. So we branch for OR. So what that means is we'll try both of the possibilities that arise because of this definition here. In the first one, we're going to try that Vincent is lawful. Okay. And we're going to see what happens. We ask, is this inconsistent? And we see that because Vincent is lawful and Vincent is a godfather and godfather is disjoint with lawful, we have an inconsistency, right? So we say Vincent is a godfather can't be lawful, Vincent is lawful. Okay. So we have an inconsistency here. So this branch is inconsistent, which makes sense. And we have to check all the branches to make sure all of them are inconsistent. In this case, we have the branch here, Vincent's lawful. Here's the one where he's criminal. So Vincent is a criminal. Vincent is not a criminal. Okay, this is a very direct inconsistency here. So this is also, branch is also inconsistent, which means that this ontology here, O and not O prime, is unsatisfiable, which means that O entails O prime. So in this way, we can do reasoning over disjunction. Basically, what it means is we're going to try all the possibilities and see what fits, right? See if everything makes sense. So with this, we can get this sort of inference as we saw here. Another example would be to take a different example. Here we ask, is Vincent, so Vincent is lawful. Is this entailed by the ontology, right? So we have the same ontology, and now we're asking a different question. Is Vincent lawful? Is it entailed? So we apply the same procedure, right? We have the same ontology. This time our inference has changed. It's not Vincent type lawful. So we're negating the entailment. We want to check Vincent is lawful. We negate it, add it to the ontology. And then we check each of the branches and we see, okay, let's assume that Vincent is lawful. What happens? Well, this is inconsistent, right? So that's first branch down. What about the other possibility when Vincent is a criminal? So when we say Vincent is a criminal and Vincent not lawful, if we look at this, we find no inconsistency. There's no obvious inconsistency here. So it means that essentially this branch is okay. Yeah. So because not all of the branches are inconsistent, it means that the original ontology, this thing here that we've created, O and not O prime, is possible, right? It's satisfiable. So it means that the entailment does not hold. So again, here we need every branch to be inconsistent. Any questions or doubts? Okay, so what the Tableau is doing intuitively is just, there's multiple possibilities that arise. It tries all of them. If it thinks that something exists somewhere, it adds it, right? So it's somehow just trying to expand out all the knowledge and see what happens when it does that. So in this case, this is not entailed, right? Because somehow the ontology that we're checking here is satisfiable. It's perfectly reasonable to speculate this, right? There's no contradiction. So because of that, this is not entailed. So we see an example of entailment and not entailment. Back to our worst example of the course award. So here we have again that Michael is a parent, and a parent is someone who has a child. Is a person, is someone who has a child that is a person. Okay, so we're assuming that parents are people in this case, and that has domain fertile. So someone who has a child is fertile, and then we imply that Michael is fertile. Okay, so how does this work? Essentially, we don't get this from rules because we never state that Michael has a child, even though we know it. We know that something exists, we just don't write it down in the rules, because if we start writing down these existentials, it could go to infinity. right? But what we do in the Tableau algorithm is pretty straightforward. When we have this sort of thing that we know that Michael must have a child because Michael is a parent, we propose a hypothetical child. We'll just say, okay, let's say Michael has child X, right? Which we could also, represent with a blank note, for example. And that X is a person. Okay, so we can expand out that, and it doesn't really matter what X is. We know that Michael has some child. And then we check to see if this is inconsistent or not. And we see that it is, because when we say that Michael has a child X, then we say X is of type person, according to the definition here. And then we say has child domain fertile. And since Michael has child X, it means Michael type fertile. And this contradicts with the negated form of the entailment, right? So essentially what happens is if we have these sorts of something exists, then we just add something. Doesn't matter what it is, we just put some element there and say, okay, we have X in that position. And we continue in the same way. So this is inconsistent, which means that the entailment holds. So unsatisfiable in all branches. There's no disjunction here. It's just one branch. Therefore, O entails O prime. And we have this entailment here through this Tableau algorithm. So as long as, again, O and O prime follow the restrictions, we are guaranteed a correct answer to O entails O prime, to deciding O entails O prime. And one way we can do that, or even prove that, is with the Tableau algorithm. We can show that this algorithm will generate the correct answer and will always hold for this type of entailment. Okay. Essentially, I mean, what I showed here is a very brute force way of checking models, looking to see if a model can exist or if an ontology is satisfiable or not. It's just, trying to expand out all the knowledge, trying to expand out all the possibilities and that. But there are some optimizations, and there's some tricks possible to kind of prune branches that are going to result in inconsistencies. You can also use tricks for specific logics, like the logics, the DL logics or OWL. And there are methods based on, for example, hyper Tableau that optimize this process, try to use some clever tricks. But in general, it's not going to be efficient, because if we have lots of different possibilities combined with lots of other possibilities, then it quickly becomes, we can have exponential kind of exponential different branches to check. So that leaves us with one last question, which is in this third option, the whole point is that we're going to restrict what ontologies we accept, so that we can say, okay, so long as the ontologies follow the restrictions, we can do reasoning over them. So that creates a sort of a doubt in this case. Because it means there's a question here of why do we restrict OWL in that case? Why do we restrict OWL if essentially we need to, if reasoning is so expensive, right? So we can ensure that the Tableau algorithm with some tricks terminates, right? It will finish. So we have a sound and complete algorithm for that. So that's great, but there is a slight kind of problem with this, right? So we have this with the Tableau algorithm or a similar algorithm, we have a complete entailment algorithm that supports a lot of OWL features and always terminates. So it'll always work. We can do reasoning over it, right? And we can express a lot of things in it, which is great. But so it's great. We can now get these sorts of inferences here where we know that Zia is a Zeproid. And we can entail this with Al2DL, and this is all of the definitions we saw before we can do in Al2DL, and it will tell us, if we put this into a Al2DL reasoner, it will actually tell us that Zia is a Zeproid, because we expect it to be complete in some way. So what are the problems with this sort of approach? There are a few practical problems. So the first is that here we're assuming that we give the entailments to check. So we cannot just ask to compute the entailments. Well, we can ask, but all the entailments are infinite. So it's, we can never be complete because we can never write down infinite entailments. So, okay, that's, it's only complete for the entailment decision. So asking is if two ontologies, one entails the other or not. Restrictions are complicated. So they're the restrictions needed to make sure that an ontology is an L2DL is very complicated, often broken by real-world ontologies. And Tableau entailment checks are really expensive in theory, in the worst case. So branching for every disjunction, if you imagine all these branches is, Vincent criminal or lawful? So let's say we had 4 people and we know that each of them is criminal or lawful, right? That creates 2 to the 4, 2 to the power of 4 possibilities, right? An exponential number of possibilities, where each one of them is, each one of the 4 people is either criminal or lawful. And then we have on top of that other things like counting and cardinalities and existentials and so forth. So actually this entailment checks that we're doing here using Tableau. But in general, the general problem of entailment checking for L2DL ontologies is N2 time complete. So what does this mean? It means that if you had a non-deterministic machine that was very good at guessing correct answers to things, even with that machine, it would be doubly exponential. So it would mean it would 2 to the power of 2 to the power of n on that machine, guaranteed, right? So such a machine doesn't exist. So this would be 2 to the 2 to the n. So you could actually add another exponent here, right? So essentially it means that it's very, very, very expensive in the full language to do reasoning. So with this third option, okay, entailment is guaranteed to halt in theory for all ontologies. It will return an answer. We have an algorithm that will return you a correct answer. It's eventually, in theory, the problem is that the halt in practice might not happen before the heat death of the universe, right? So we might essentially have reached the end of all existence before the reasoner gets to return. So there's this question about this third option of, is it really practical to restrict the language? Because, okay, we restrict the language and now the reasoning problem is decidable, but it's so expensive that there might not be enough time for it to halt, right? So it's sort of like we inherit some problems from the other options as well. So, okay, but in theory, at least it would halt. So how do people get around this? There are some other sub-languages of L2DL that don't allow you to define as much, but that are more efficient for reasoning, that provide some sort of notion of tractable or polynomial time reasoning. And these are L2RL, which is the restriction of L2DL such that the rules that we saw previously are complete. L2EL, which is a tractable algorithm just for classifying ontologies, saying what classes are subclasses of what other classes and classifying instances and so forth. And L2QL, which is something, ontologies that you can support by rewriting SQL queries or rewriting, let's say, Sparkle queries. So you take one query and you just expand it to create an expanded query that will return you answers with the entailment. So we're not going to get into those details. Any questions or doubts? Okay, so this last part here of OWL, you see that there's a lot of kind of stuff going on, right? And this is really where the research, there's a lot of research been done, and there's still a lot of debate in the research community about what's the best way to proceed. And there's a big division here between theory and practice. In the theory side, you have the people who've worked on description logics for a long time, and they like their theoretical notions like decidability, and they like to maximize the expressiveness. So let's say, what's the most expressive ontologies I can have with NP complete reasoning? What are the most expressive ontologies I can have with P space, polynomial space time reasoning? These sorts of things. So packing as much into a complexity class as possible. Whereas in practice, you don't really care so much about the complexity. You just want your ontology to reason in quickly, right? So it might be the case that you have a decidable reason, or you have an algorithm that will terminate, but if it's still running after 4 months, it's not very useful to you, right? And there's some gap here in terms of how to manage this sort of situation. as is common in computer science in general. There's always a sort of gap between practice and theory that can be difficult to bridge. Yeah, so in general, it's not something just about the semantic web or about OWL, but there's this general topic of knowledge representation. So here we're looking at knowledge representation on the web. What we see here is essentially there are limits to what machines can reason about, or what algorithms can prove. Okay, so this is the end of the OWL classes. So probably the more, how would I say, the more advanced topics of the class. Next, we're going to move on to SparkPool, and then we're going to move on to validating RDF. But first, we have the lab. Any questions or doubts? No? Okay, so what we're going to see in the lab today, what I wanted to really get across here is the difference between the rule-based reasoner that we've been using before and this Tableau reasoner, which will give us, if we use the rule-based reasoner, we'll see that sometimes it will miss things that we're expecting. In the L2 DL reasoner, in theory, it's somehow in some way complete, right? So we're going to use a reasoner today that's different. It's a DL reasoner. It could give us this sort of inference here. And we're going to use it for the last lab, and we're going to, the lab will be based on cardinalities mostly, but different types of axioms. So we'll move to Discord.